In that case, we'll crack on. So, thanks to Simon's wonderful introduction. You're all aware my name's Lucy, I'm a geologist by training, and today I'm going to talk to you about lithium. But hopefully by the end of this talk, we'll have a sense of why lithium's so vital, the role that it's going to play in this energy transition, or is already playing in the energy transition. And then I'll talk a bit about the work that we're doing down in Cornwall, exploring lithium. And if you have any questions, please do. I think we'll have time for them at the end, so please do feel free to ask whatever you like, and I'll try my best to answer it. So this disclaimer: you are welcome to ask. Just one minute out of the way. So, to set the scene, I want to talk a bit about mining, and it's something that's probably, well, it's very close to my heart. I spend a lot of my day thinking about minerals, how to find them, how to extract them responsibly, how to process them, and it seems completely obvious to me that they're integral to our daily lives. But I think something that geoscience, the mining industry, the extraction industries in general are suffering from are quite a negative public sentiment. But everything that we use in our daily lives has either been grown or it's been mined. And I think as a sector, as a specialism, we've got a real job in front of us if we're to convey to the general public quite how crucial geoscience is. It's important for our houses, for where we live, our energy, how we move around. And as geoscientists, I really believe that we've kind of got a role as stewards of the Earth. We understand how the Earth systems work, we understand where these resources are that are so vital to our daily lives, and we understand how to extract them. So I think we've got a really significant role to play in doing that as responsibly as we possibly can. So probably preaching to the choir here, but just trying to get across that everything we use has been extracted from the Earth in one way or another. And as we go through this next energy transition, we've actually got, sorry, my slides aren't moving for some reason. We've got a real job in front of us if we're going to be able to find these resources. So people are talking about the fourth industrial revolution, or the energy transition, as we move away from a carbon-fueled society to one where we're harnessing renewable energy instead. And that requires us to deploy low-carbon technologies such as wind turbines, or maybe solar panels or batteries to allow us to store these energies. And actually, we're using a whole suite of minerals and metals and elements of the periodic table that we haven't necessarily used in these quantities previously. As technologies develop, they become more and more specialist, and we're starting to need to find a lot more of these elements within the periodic table that maybe 50 or definitely 100 years ago we weren't using. So these low carbon technologies include things such as wind turbines, it might be solar panels, and battery technology to store this is going to be really crucial. And something that's sometimes missed out of the debate talking about the energy transition when you hear it on the news or you see it in newspapers is quite how mineral intensive it's actually going to be. So mining is going to be a crucial part of delivering this energy transition, because we need the raw materials if we're going to be able to build our solar farms, or if we're going to be able to build our wind turbines. And this statistic here, we reckon that global renewable capacity is expected to grow by over 1 terawatt by next year from just 2018, which is a nearly 50% increase in just 5 years. But a coal-fired plant or natural gas, that actually requires a lot less technology or infrastructure than these new renewable energies. So this statistic here, an onshore wind plant requires 9 times more mineral resources than your gas-fired power plant. An electric car has 6 times the mineral inputs of a conventional car. And actually, because we're moving to using more and more renewable energy sources, and these are energy intensive to create, then actually the average amount of minerals that we need to generate a new unit of power has actually increased by 50% as the share of renewables has risen over the last decade. And so why are we doing this? Why are we trying to move away from carbon fuels? It's because we want to combat climate change. Last year's IEA, International Energy Agency report suggested that if we want to actually reach the goals of the Paris Agreement, which is climate stabilization at less than 2 degrees, oh, it's supposed to be a little zero there, but if we want to stay below 2 degrees of global temperature rise, then actually we need to quadruple the amount of minerals we're producing for clean energy technologies by just less than 20 years' time. If we want to reach net zero globally by 2050, then we need 6 times more mineral inputs in 2040 than today. But in the mining industry, the average time now, once you've found a deposit, and I'm sure we're all aware that finding a deposit can take years, if not decades, and once you've found that deposit, the average time to now bring that into commercial production is actually 16 years. So if we're to find 6 times more mineral inputs by 2040 than we're currently producing today, as an industry, we've got a huge job ahead of us. And that's why it's going to be so important to embrace new technologies to allow us to explore for things much more efficiently, new technologies to allow us to extract things much more efficiently. But that's why concepts such as the circular economy, reusing things, designing things for second life, recycling and recovering all of those minerals and materials that are currently in circulation or might be residing in landfill or not being recycled currently, then all of this is part of this bigger jigsaw puzzle, but we've got a long way to go. So this is an infographic that hopefully you can see. It's from the World Bank. They have an initiative called Climate Smart Mining, and it's looking at, okay, we need to find and we need to extract a lot of minerals over the next few decades if we want to be able to support this energy transition through building these low carbon technologies. So how can we ensure that we're doing this as responsibly as possible? The World Bank actually forecast a nearly 10-fold increase in lithium demand from 2017 to 2050. I think that's probably gone up since then. They also predict that in that same amount of time, we're going to be needing 585% more cobalt, though people are looking to minimize the amount of cobalt that's being used in lithium-ion batteries, for example. And they're also forecasting a 7% increase in copper demand from 2017 levels. But what really surprised me on that, and hearing that statistic, was that if you can see in this last bottom corner here, in the last 5,000 years, humanity has mined about 550 million tons of copper. The World Bank estimate that we will need that same amount of copper again in the next 25 years just to meet global demand. And that's just mind-boggling. So as an industry, we've got to be able to ramp up production to meet this demand. So we need to be finding new mineral deposits, ideally a few years ago. But we've got a real role to ensure that we're extracting this mineral resource as responsibly as we possibly can, whether that's environmentally responsibly or socially responsibly. If mineral extraction is done responsibly, then it's got the opportunity to contribute positively to all 17 of the UN Sustainable Development Goals. But obviously, as I'm sure we're all aware, there are potential challenges in delivering that in certain parts of the world, and perhaps it requires us to rethink how we value these mineral resources. Instead of just looking at projects with a monetary lens, maybe we need to start thinking about how do we quantify those environmental and social impacts in a way that affects project development perhaps more efficiently than our current systems do. And the other key point is that mining accounts for up to 11% of global energy use. So, nearly, it's between 5 and 11% from what I can find on the internet. So if we can decarbonize that energy that's being used by the mining industry, then that can have a really significant impact too. And so much of that energy goes on crushing rocks. So again, if we can be more efficient in how we extract our ore and make sure we're extracting much less waste rock, then that's surely got to be a good thing. And something that I really can't get my head around is, there are gold mines out there that are economic to mine at less than 1 gram per ton gold. Like, it blows my mind that we still think that that's okay. But anyway, maybe that's a conversation for a pub. So this again is a diagram from the IEA report that came out last year, and it's got some fantastic statistics within it. And it's just illustrating this fact that the new technologies that we're looking to deploy to help us move away from our reliance on fossil fuels really do require a whole suite of minerals that we haven't necessarily been using in these technologies before, but also it requires much more of a mineral input than these traditional coal-fired or fossil fuel-fired plants. But to put it into perspective, these energy transition minerals are still a relatively small market if we compare that to coal. So last year, the revenue from coal was 10 times that of the revenue that was generated from energy transition minerals. And you can see that in the 2030 and then 2040 scenarios that the IEA predict here, they reckon that, by about 2035, the revenue from energy transition minerals will have overtaken coal, but that's still quite a mark, that's still 15 years away. Is it? Nearly. So where are we going to find these raw materials? Where do they currently come from? Well, at the moment, we've got global supply chains. And, global supply chains can be great because they can force us to cooperate with our neighbours, which is wonderful. But as we've just seen with the recent Ukraine crisis, for example, they're subject to factors that are often out of our control. And actually, if we're shipping things all around the world, there can be fairly significant carbon impacts associated with that as well. There's also geopolitical risk with some of these supply chains. The Chinese, for example, have been incredibly clever at developing the capability to refine a lot of these technology critical materials. They might not be producing them in China, they're obviously rare earths, we all know that story, but even if they're not producing the primary product, a mineral concentrate there of lithium or cobalt or rare earths, actually they've got most of the world's capability to refine those into cathode precursor materials, for example. So they're adding all that value, but it also means we're totally reliant on them for a lot of these critical raw materials. So we need to be able to look into more remote places. So this is where skills such as using satellite imagery are going to become really important. Using data science to allow us to take in massive global data sets and start to develop algorithms and ways to use machine learning to perhaps vector in on areas that might have potential for buried large copper deposits, for example. And there's a lot that I think the mining industry can probably learn from the oil and gas industry when it comes to dealing with these big data sets and predicting where we might want to look next. But then firstly, we might need to look closer to home as well. We have mineral resources in the UK, Northern Europe and USA, but actually we also seem to have quite a lot of this NIMBY, not in my backyard attitude. We've been offshoring and outsourcing the impacts of extracting all of the materials that we've been using over the last couple of decades in a lot of these places. So maybe there is an argument that we should start to take some of that responsibility back on ourselves, and perhaps when scope 3 emissions become more and more important to report, that's going to come into play anyway. But if we've got mineral resources on our doorstep, we've got high environmental standards, we know that people are paid fairly and well, and we've got high labour laws and human rights, then actually maybe there is an argument for looking at these resources that might be closer to home as well. And it all comes back to we've got an opportunity to do something right and to do something really good and bring a lot of parts of the world and communities along on the journey with us. So we need to make sure that we're doing this as responsibly as we possibly can. So I'm going to focus on lithium for the majority of this talk now because it's what I know a bit about, and that leads me on to being able to talk about the work we're doing down in Cornwall as well, which hopefully will be interesting to some of you. So to set the scene, the Faraday Institution estimate that we're going to need 75,000 tonnes per annum of LCE, so lithium carbonate equivalent. It's the way that people quite often report lithium units. So we're going to need 75,000 tonnes per annum lithium by 2035. And if we look at this graph here for 2022, you can see that at the moment, the demand is pretty much at supply, there's already a bit of a deficit in the market, and that deficit is predicted to continue, barring a couple of years in the future, as we move on through the next decade or two. So at the moment, demand is slightly outstripping supply, but they reckon that perhaps by the end of this decade, demand's going to overstep the current supply that's in the pipeline. So the automotive sector in the UK is really important to our economy. It employs nearly 800,000 people directly and indirectly, and generates about, well, there's about a $60 billion turnover for the industry as well. So as we transition to having electric vehicles instead of traditional combustion engine cars, the UK needs to transition to producing electric cars if we're going to maintain that market share. But currently, we're completely reliant on importing all of these raw materials. And actually, if we're importing all of these raw materials, we don't tend to import them as raw materials. We're importing them as batteries that have already been made up. And if we want to have ownership of those supply chains, and I think after the silicon chips that's been causing a lot of issues for the car industry recently, after the crisis of getting hold of those for the last couple of years, we're seeing a real change that car manufacturers are starting to look much further upstream for their supply chains and want to at least have oversight of, but actually perhaps ownership of what those supply chains are looking like too, so they can try and minimize any future supply chain disruption for electric cars. So if we can produce not only the batteries in the UK, but maybe some of the raw materials that go into those batteries as well, then that could have real security of supply benefits. If we're not shipping these batteries and the raw materials that go into them all around the world, and we're producing them to high environmental standards that we do have here in the UK, then that could have environmental benefits of it. And then thirdly, the rules of origin. Brexit, I'm sure we all have opinions on Brexit. I personally am not sure who voted for it, but the rules of origin that are coming into play post-Brexit mean that if we want to enjoy tariff-free or low-tariff trade with the EU, then we've got to be producing things domestically, or we've got to be producing a certain proportion of the value of what we want to sell domestically. And as the unit cost of producing batteries is coming down, the relative cost of the raw materials, and so the lithium within those batteries, is going up. So if we can produce that lithium domestically rather than having to buy it in, it's going to potentially have a significant impact on the rules of origin as well. So this all adds up to, it's a pretty enticing climate to be trying to develop lithium projects in the UK. You might hear the baby in the background, so sorry about that. So where do we currently find lithium? This is a map of the world here, and you can see that there are some hotspots over South America and West Australia. So in South America, we have the lithium triangle, and that's where we find a lot of lithium contained within salar-type brine deposits. So these are really arid areas, generally, places such as the Atacama Desert, where you get these salty brines that form just below the surface. They'll pump them up to the top, and then quite often they're processed by very, very old technology, relying on solar evaporation. You have these huge evaporation ponds, and your salty water is pumped up to the surface, and over a period of 18 months, 2 years perhaps, enough water evaporates off that you have a super concentrated salty fluid, and then you'll process that to extract your lithium salts, generally lithium carbonate, from those brines. If we go over to West Australia, we tend to have a lot of a mineral called spodumene. So spodumene is a hard rock mineral. It's generally found in kind of pegmatites, and you mine it generally through open pit mines. And classic mining, you crush the rock up, you separate out the spodumene, and then if you want to extract the lithium from the spodumene, there's generally a roasting step. So you might have to use fossil fuels to roast your rocks up to north of 1,000 degrees Celsius, cracks the crystal structure and lets you leach out the lithium. But there's obviously quite a high carbon impact associated with that roasting step. Lithium I'm sure you all know, is not actually that rare, but finding it in places where it's concentrated enough to let you, or to make it economically viable to extract, is different. And finding technologies to, well, because this demand for lithium has been projected for a good few years, and we're seeing a tangible uptick in demand at the moment. Over the last few years, there's been a lot of research going into extraction technologies for what have previously been considered unconventional type deposits, whether that's lithium in geothermal waters instead of salar type brines, or lithium in mica minerals rather than in spodumene. So in Cornwall, we've got what have previously been thought of as unconventional mineral deposits. And so it really is the advent of new extraction technologies which are unlocking their potential. So that leads us on to 21st century exploration. Cornwall's got this amazing mining heritage. We've got evidence of mining going back for thousands of years. There's the Nebra Sky Disk, which I think is currently on show at the British Museum, which I'm planning to go and visit next time I'm in London. And I think this is supposed to be one of the first depictions of the night sky. And it's, oh God, I'm testing on this, 3,500 years old. It's old. And what's fascinating about it is that some research was done a couple of years ago looking at the provenance of the metals within it, and it contains gold from the Carnon Valley in Cornwall, but then it contains tin from Germany, I think copper from somewhere else, and it shows that there was evidence of metal trade going on at this point in history across Europe, which is pretty amazing. This shot on the left is from Vitalik, which is out west in Cornwall, and the mines at Vitalik, the shafts that drop down, they then mined out underneath the sea, and there's stories from the miners that when it was stormy and there were waves crashing around, they could hear the boulders rolling around on the seabed. It must have just been absolutely terrifying. But Cornwall, historically, it's been a globally significant mining district. It's produced over, these are statistics from the World Heritage Site in Cornwall, the Cornwall and West Devon Mining World Heritage Site, which trips off the tongue. And a few years ago, they worked out that Cornwall had produced over $50 billion of tin in today's money, over $12 billion worth of copper. I mean, I think the tin price has either doubled or tripled in the last 12 months, so it'll be a lot more now. But, we didn't run out of ore in Cornwall when mining stopped. It just became more expensive to do it here, and the easier stuff at the surface had perhaps been accessed. But in light of new technologies, and in light of our demand for metals that we weren't even looking for even 20 years ago when the last tin mines shut, then there's real opportunity down here still. So this on the right-hand side is a section from United Mines in central Cornwall, where I think copper was the predominant metal that they were mining. And you can see that there are two narrow, steeply dipping veins, hopefully. There's a big Elven dike, which is just a microgranite dike which cuts through it, which is slightly shallower. And it says that the temperature of the deep levels in this mine is remarkable. And what's interesting is that in these deep levels of the mine, they had ingressing hot springs. And these hot springs flowed into the mine at constant flow rate for 25 years. They've got water of 110 degrees Fahrenheit, which is about 45, 50 degrees C. And these hot springs were found all across Cornwall in the deep mines. And the reason that they started to pinpoint the location of these upwelling waters into the deep mines initially was because it was a welfare issue. It was hot, it was humid, and so people couldn't work at these deep levels for very long. So they wanted to try and understand where they were springing up and why they were there. So going back to that section on the right-hand side, the key bit that I forgot to mention is that last sentence. The hot water issuing in great quantities at these depths is rich in lithium. So this is from 1864. Professor Miller from King's College took some samples of these upwelling warm waters at United Mines, took them back to his lab in London, analysed them, and found that there was an unusually high amount of lithium in the water, which was academically interesting at the time. He wrote a paper about it and said, these hot waters could be a potential source of lithium. It's just a shame that we don't have a use for it. So fast forward to 2022 or 2016, Jeremy Rathall, our CEO, was doing some research about lithium. He trained at the Campbell School of Mines and has maintained strong links with Cornwall ever since then. He's a mining engineer by training, and he had been involved in trying to reopen a Cornish mine, and that hadn't worked out for whatever reason. But at the time, they'd been talking and said, oh, we've got everything in Cornwall. It's not just tin and copper. We had cobalt mines, there's gold from the Carnon Valley, but also there's lithium in these upwelling warm waters. And that led him to do some research back in 2016 and gave him enough confidence in what he found to found Cornish Lithium. So I joined the company back in 2017, which is it is 5 years ago, which is terrifying. And we've been looking for lithium in Cornwall ever since. And we've now got a team of over 50 people down here. We're focused on looking for lithium within geothermal waters, but we're also looking at the potential to produce lithium from the granite rock itself. So I'll go into that in more detail in a moment. But how we're doing that is very much inclusive of this amazing mining heritage in Cornwall. There's evidence of mining going back for thousands of years, but because there's been commercial extraction of tin and copper for hundreds of years, and there are family archives out there, there's the County Records Office, we've got access to an amazing amount of information about the subsurface. And so we have a whole team of archivists who capture the information from these old maps, plans, sections, records, digitize them and bring them into GIS, into a format that our geologists can then use to explore. So this is an example of a section through a mine. You can see that there's a couple of boreholes and there's a mineral lode that they've drilled into. And it's got lots of notes and everything on it as well. So we can bring that into our 3D modeling software. We use Leapfrog. We can kind of virtually hang it in 3D space because we know where that point is on the surface, that point is over there, and then we know the depth. Then we can trace on all of the geological features that we're interested in. We can then do that all through the mine because these sections were done at, say, 100-meter intervals throughout the mine. And that allows us to build up a 3D model of the geology, the mineralization and the structures. And then we can also add on where these upwelling warm waters were, for example. So that historic information is such a powerful tool for us. And it means that we can have this understanding of the subsurface without having to do lots and lots of drilling, which is expensive, as we all know. But that's not the only tool available to us. We're also using whatever data we can get our hands on. So satellite imagery has been really key. We've done a number of innovation projects with the Satellite Applications Catapult, looking at how viable it is to use different types of satellite imagery and processes in different ways to try and highlight features that we're interested in, whether that's mapping geological faults or whether it's trying to map different clays and seeing if that alteration has any impact on what we think the mineralization might be at depth, for example. We've then flown drones and taken 3D surveys of the cliff face. So on the right-hand side here, you can see that there's a steeply dipping, or slightly sinuous fault that's outcropping. There are big geological faults that come all across Cornwall, and these are of interest to us because it's these big geological faults that are permeable, and these act, we believe, as the conduits for these deep groundwaters, these geothermal waters to circulate at depth. So Cornwall's pretty highly vegetated, and you can't see much geology. There aren't that many rocks that outcrop at surface in the centre of Cornwall, but if you go to the coast, go to the cliffs, then it's a real opportunity to see these. But by flying drones, and if you use a GPS and get a really accurate few GPS points, you can effectively fit your model and rotate it to exactly where it is. And then that means you can actually take pretty accurate structural measurements from planes on that 3D model virtually. Obviously, it's no substitute for going out in the field and clambering over the rocks, but if it's at the top of the cliff and there's a couple of structures that you really want to measure, but it's completely unsafe or just not possible to reach them, then this is a great alternative. Geochemistry plays a really important role. We've got historic geochemical information about these upwelling hot springs that was taken, and we've also been taking a number of water samples ourselves, whether that's from places of interest or upwelling springs, or from our drill programs that we've been doing. And there's also soil samples and soil surveys available to us. There was the TELUS survey that was flown in 2014, I think, with the BGS. So that gave us airborne geophysics, but it also was a kind of Southwest England-wide soil sampling program and a stream sampling program and a stream sediment sampling program. So that data is all really useful, and that's actually all publicly available as well, which is pretty cool. And then field work. These are some nice scenic shots of the field. You can see some of our guys even went out in kayaks to try and map some of these structures and get a picture of it from the coast. I've been out in the field today and it was grey and about 11 degrees and wild wind and driving rain. So Cornish fieldwork can be lovely, but can be awful. So that's kind of setting the scene as to how we're looking for things. But what are we actually looking for? So Cornwall has this big mass of granite that underlays southwest England, and it's called the Cornelian batholith, and it stretches from Dartmoor in the east all the way out to Land's End and then the Isles of Scilly in the west. And this granite was intruded over about a 20 million year period, from about 290 to 270 million years ago. And there are certain pockets of that granite that are more enriched in lithium and other volatiles than the others. One of the classifications that we use calls it the G5 granite, because there's kind of 5 broad species of granite, I suppose. It's one way of thinking about it. And so we believe that the reason that there is lithium within these geothermal waters is because these deep groundwaters have been circulating throughout this mass of granite at depth within this fracture network for thousands of years, and effectively leaching the lithium from the lithium-rich micas in the granite into the geothermal waters. Although there's bulk lithium mineralization throughout that whole granite, there are certain pockets of this, slightly later in place granite that are more enriched in lithium mica minerals than others, or the lithium's more enriched in the micas. One such place is the TRELAVOUR project. So this is our hard rock lithium project, and it's located in the St Austell area of Cornwall, if any of you are familiar with Cornwall. And St Austell is famous for its china clay industry, and we're actually looking in an existing china clay pit. So what we're planning to do is repurpose this china clay pit, which hasn't produced china clay for well over a decade, and actually produce lithium from it. So it's open pit mining. We've done a couple of rounds of drilling so far, and we've got an initial JORC compliant resource which shows potential for a 20-year mine life. You can see here it's approximately 51 million tonnes at 0.1% lithium, with co-products of rubidium, potassium and cesium. We're planning to do some more drilling in the not too distant future, and that's to potentially expand the resource, but also expand our confidence in that resource. So we're looking to move from inferred to indicated, for example. And it's an old china clay pit. It's already an open pit. So thinking of social license to operate, it's already an open pit. So we're just looking to continue working that open pit, which hopefully gives us an advantage. The community so far have been very supportive, but that's not something we take for granted. That community support, social license to operate, is absolutely vital. And we've been trying really hard to have a kind of open, transparent relationship with the communities. Like, we all live there. It's not like we're flying in to work on a project and then flying home again. I want to be able to turn up to the pub and hold my head up. So we need to be honest and transparent about what we're doing. But where was I going with this? Yeah. So we think that there's an advantage because it's an existing china clay pit already. There's also a skilled workforce in the area who've been mining china clay for decades. Well, china clay mining's been happening for 275 years in Cornwall, in this part of Cornwall, and it's been ever so slightly in decline over the last decade or so, it's probably fair to say. And so the potential for jobs and a skilled workforce for some of these jobs on our doorstep is also a huge advantage. And there's also mining infrastructure that we might be able to use in the region too, such as industrial railways, for example, and ports that are fully set up for loading minerals onto ships. So we're hoping, with a fair wind and a fair permitting and planning wind, that production might start as early as 2026. But obviously, we've got quite a lot to do before then. We're looking for lithium contained within mica minerals. And as we mentioned right at the start, mica minerals are kind of considered a fairly unconventional lithium resource. And it really is the advent of Lepidico's processing technology that we believe has unlocked the potential of the St Austell granite for lithium extraction. So what's really important to us is that there's no high temperature roasting step. And so we believe that that should have, hopefully, a positive carbon impact. So we should be producing less carbon by producing the lithium this way. What's also really exciting about it is that it allows us to produce a lithium hydroxide product that's battery quality, battery grade, on site as well. And so rather than producing our mineral concentrate on site and then having to ship it elsewhere to upgrade it to something that's of a quality to go into a battery, we should be able to do that all using this Lepidico site, using this Lepidico process, which is really exciting. And then we've also got the potential for co-products, so rubidium, potash, cesium, and it's really important to us that we try and minimise our waste as far as possible. So there's significant potential for pretty hefty volumes of aggregates as well. So we want to do everything we can to maximise the byproducts from this. There are economic reasons for doing that, but there are environmental reasons as well. Minimising your waste is pretty key. And finally, that ties really nicely into this circular economy model, minimising your waste as possible, being as efficient with this resource. If we're extracting this rock, what else can we get out of it? So our second project, or say second project, the company was founded actually to look at the potential for producing lithium from these geothermal waters. And these geothermal waters circulate naturally at depth within these permeable fault systems. And we have evidence of that going back 160 years, that section from Professor Miller that I showed you at the start, which says that there are hot waters issuing at great depths and they've got lots of lithium in them. We've got evidence of that from a lot of mines all across Cornwall. How do we access these now? Well, we can access them by drilling boreholes from the surface down to depth, intersecting these geological structures at depth, pumping them back up to the top, and then we're looking to use a new suite of technologies called direct lithium extraction, which allows you to selectively remove just the lithium ions from the water, but I'll show you a slide on that in a second. So to date, we've drilled 2-kilometre deep research boreholes and intersected a number of permeable geological structures with those boreholes, put those waters back to surface, ticked off that they were warm, ticked off that they contained lithium. We're currently nearly 1,500 metres into another borehole, and we've gone through a number of permeable structures within that, and again, they've got warm water and it's got lithium in it, which is fantastic. That was the aim of the game. And what we're seeing is that we think that there's probably a sweet spot somewhere between 1,500 and 2,000 metres deep. We've got the granites in Cornwall are important not only because they're bulk enrichment in lithium, but also because they're hot. So we've got the highest potential, we've got the highest geothermal gradient in southwest England compared to anywhere else in the UK, which is why we've got significant potential for geothermal energy. So there are a couple of projects that have drilled down to about 5 kilometres depth, and their ambition is to produce geothermal power. There's one called the United Downs Deep Geothermal Project, which we drilled a few years ago, and they're in the process of commissioning their power plant, I believe. And there's also the Eden project, Eden Geothermal, drilled down to about 5 kilometres last summer, and they're looking to put a power plant in there as well. But drilling down to about 5 kilometres requires oil and gas technology. It requires huge rigs. It's orders of magnitude more expensive than a mineral exploration rig. And yes, you'll get geothermal power. You'll get hotter waters. The deeper you go down, the hotter it gets. The more stuff there is dissolved in those waters as well. So you do see that the lithium grades are higher. However, we think that the sweet spot would probably be somewhere between about 1.5 and 2 kilometres, because it's orders of magnitude cheaper to drill to that depth. Your water's still warm, you've still got appreciable amounts of lithium in those waters, and so geothermal heat is also going to be a significant byproduct. It's not hot enough to generate power, but it is hot enough to use that heat to potentially decarbonise other industries that might need it, decarbonise agriculture. You know, heating accounts for 37% of the UK's carbon emissions. So if we can decarbonise heat, might be through district heating schemes for houses perhaps, then that's a real opportunity as well. And we've got a couple of partnerships in the pipeline that are looking at that at the moment. We've also got an amazing facility that's been set up at United Downs at our test site there, where we're currently running a pilot plant to allow us to trial some of these direct lithium extraction technologies. So rather than having to use evaporation ponds to allow us to concentrate up our lithium-rich brines, it rains far too much. It's currently raining out there and it's horrible. But also there are much more efficient technologies out there now that look like they'll be really suitable for use on the Cornish waters. These kind of come under the umbrella of direct lithium extraction technologies, or DLE technologies, and they kind of fall into two camps. One is either a membrane, so highly selective membranes that allow you to just remove your lithium ions, or kind of sorbents, so an ion exchange mechanism, for example. We've been granted some funding from the government through the Getting Building Fund. I say it's a £4 million government grant here. It was a £4 million project, of which 2.9 million has come from the government, and we funded the rest. So that pilot plant is trialling a DLE technology that's been developed by a French company called Geologist. I think it's coming to the end of its trial now. And our intention is that once we've run that trial, we're going to get someone else in with their technology, and it's just allowing us to test which is most suited to the Cornish waters. Yeah, that's probably the best way to say that. So in the waters, lithium is present as lithium chloride, and using the DLE technology, we produce a lithium chloride product as well. We can go into that in more detail later. So what's on the cards for Cornish lithium then? We've got our hard rock project. We are actively moving that forward. So we've produced a scoping study recently. We're now planning another round of drilling to upgrade our resource to from inferred up to, I was completely gone from my head. But anyway, we're looking to upgrade our resource, our confidence in our resource. We're hoping to expand that resource as well. We're in the process of building a bigger than pilot scale, but not a full scale lithium extraction plant up at TRELAVOUR as well. We're calling it a demonstration scale plant, which is going to inform what our full plant will look like. So that's all progressing rapidly and is really exciting. In parallel, we're still exploring for a number of different geothermal lithium opportunities. We've got a site where we're drilling at the moment, and that's all really positive. We've got another couple at least in the pipeline. Again, it's hard to say that, it sounded like a pun. And doing this all as responsibly as we can is really important to us. So that means using new technologies to help us find these deposits, but also using new technology to help us extract them really efficiently. And ESG, environment, social and governance, is absolutely critical through everything that we do. We've talked a little bit about community engagement, which is really important to us, but also its engagement with the EA, the regulators, the planning authorities. We want to try and do this as efficiently and in the best possible way that we can, which requires input from so many different groups. We do a lot of work going into local schools. We're setting up a fund with the Cornwall Community Foundation to allow us to support local projects, but it kind of gives us that separate, it's a third party who do it, so it gives us some separation from it. And we're looking to use the expertise and the infrastructure that already exists in Cornwall. Cornwall has been a mining hub in the past. We've got the Camel School of Mines down here. There's over 100 companies in the Cornwall Mining Alliance who have expertise in mineral processing. We have expertise in social and environmental, and we're really trying to use best practice for the industry as far as we can. And this is all for the ambition of producing a stable, secure, responsibly sourced, low carbon source of lithium for the UK industry. So to wrap it up on a slightly wider scale, raw materials are so critical to this energy transition. We can't deliver it without it. And I think this really represents a big opportunity. It represents a big opportunity for geoscience, but it represents a big opportunity, if we do it responsibly, to bring those communities around the world where these projects are along with us, to train them up, to give them jobs, to create a sustainable infrastructure around it so that the positive impacts of that project will last far beyond the life of the project. And as geoscientists, we've got this big job ahead of us, but we need to make sure that there's a talent pipeline coming up behind us. And at the moment, I think that's something that we're really struggling with. We need to reframe geoscience as a great, it's a great subject to do. All of us, I'm sure, are really passionate about it, but how do we convey that to people who are thinking about what they want to study? Numbers of students applying to study environmental science is rocketing, I believe, whereas the number of students looking to study geoscience, let alone things like mining engineering, is dropping off a cliff. And part of that has got to be that as an industry, I think we've been reticent to perhaps go out and engage with schools and with younger people, and we're seen as negative and as part of the problem. By extracting fossil fuels, we've caused this climate change. Well, actually, we can't have a solution to this energy transition without geoscience. So we need to attract young, diverse people into the industry. We've got such a huge challenge ahead of us to find this many mineral resources. So we need to think outside the box. So we need divergent thinkers, and that probably means we need people from a different subsection of society, class, gender, everything. So I don't know what the solution is, but I think we've all got a real role to play in that. And it's not just people who are willing to go out with their rock hammers and find mineral deposits that we need, though that is appealing to some of us, but it's not appealing to everybody. We also need people who are data scientists. We need people who can understand life cycle assessments, mapping the carbon outputs from all parts of the supply chain, as well as the more traditional skills of mineralogy, geochemistry, etc. So I've definitely ranted on for long enough. Thank you so much for listening and your time, and for inviting me to talk. It's been a real honour. And yeah, if anybody does have any questions, I'd be very happy to try and answer them. Thank you.